The material that we're going to cover in Chapter 10 is for a different type of data set than what we've had so far. So for everything that we've had, I guess in the past couple of chapters, or really maybe the past like 3 chapters, it's always been where every individual just has one measurement, right? Either if it's for anything to do with a mean, then every individual that's in the sample, there's just one quantitative measurement for each one. And then for anything with a proportion, usually it's one categorical measurement for each one. But here, what we have in chapter 10, where we end up talking about things like correlation and regression, that only makes sense if you have at least 2 quantitative measurements on every individual. And specifically, we're just going to stick to 2. Otherwise, you end up with things where the graphs end up with extra dimensions. They end up looking really complicated. So that's what we're going to end up with. We're going to have 2 quantitative measurements on each individual. And so that's right where this begins, right? I mean, look at this right here. So when 2 quantitative variables are measured on the same set of individuals, and that's really going to apply all the way through chapter 10. So you can make a scatter plot to see if there's a trend, like if large values of one variable go along with large values of the other, things like that. So that scatter plot that's visible right here, I didn't use StatCrunch to get that one. I used R, but I'll make a StatCrunch one in a second. And there are data sets in our book where you can actually download them from the Pearson website. And that's what I did. So I wanted one where there would be a lot of data points. So just so there'd be a lot of points in the scatter plot. So I picked that Old Faithful one where there are 2 variables measured for each eruption of Old Faithful. One is how long the eruption was in minutes, and the other one is the waiting time until the next one. So what we end up with, so I graphed it where I have eruption length on the x-axis and then time until the next eruption on the y-axis. And you can kind of see the labels, right? Where like you could tell them apart, the eruption dot length and then time until next eruption. So I tried to make that as, I guess, as descriptive as I could. But how do you do it in StatCrunch? Well, it's over here on the side. So graph, that's the menu that you're going to want, and then scatter plot, and then you just have to specify your x and y variables. All right, so to go through this, let's see, there's Old Faithful. And if I copy this data, so Control C, and then in StatCrunch, Control V. So there's my data. And then if I go to graph and then scatter plot, and then the thing that was on the x-axis was the length or duration. So I'll just mimic the graph that I have in the notes. There, looks like that. And you can have a bigger one if you want, if I expand the window. Although then the scaling gets kind of weird. It might be better just to leave that as a square. But it's the same scatter plot as the one that's in the notes. So the same as that one right there. I guess it uses filled in circles instead of open circles, but same idea. All right, so when you look at that scatter plot, and really the whole purpose of a scatter plot is to see if there are any trends. So there are a couple of things that are noticeable here. One of which is that large values of one variable go along with large values of the other. And you can kind of see that just as you go from left to right looking at the scatter plot, then the points kind of trend upward. The other thing is that the shape generally is really linear, right? Like if you were going to put a best fit curve into that scatter plot, it looks like it would be a straight line. So that's something else that's noticeable. And then it's like there's a thin part. So kind of in here, like there's an area where there really aren't a lot of points, right? Like there's like a concentration toward the lower left and another concentration toward the upper right. But then in the middle, it's like there's this thin area that's almost like a gap. And I guess maybe that's something worth exploring too. As far as the regression analysis that we're going to do, we're not really going to get too into that, like on what that gap would be. And usually that's just a context-based thing where maybe there's some reason why it's tough to get eruption lengths that are that long. And I guess then that would just kind of turn to a geology question. But The big thing is really, I guess, the overall trending upward, and then that it looks linear. All right, so a positive association is what that's called, where the scatter plot trends upward from left to right, or in other words, large values of one variable correspond to large values of the other one. So if you want to think of it as if you put in a best fit line, it would have a positive slope, right? Because that's a line with a positive slope. That's what it does. It goes upward from left to right. So like if you were going to put a best fit line to this thing, I think I can kind of draw one in. It would sort of go like this, right? So that would have a positive slope. So positive slope goes with positive association, and as you would probably expect, then negative slope goes with negative association. So if you have a scatter plot that as you go from left to right kind of trends downward, then that's a negative association, kind of like how that's what a line with a negative slope does, right? As you go from left to right, a line with a negative slope goes down as well. All right, so then what if you kind of don't have either? That's when you have no association. Usually what that looks like, let's see, I guess I have enough room to draw one in. Usually it just doesn't look like anything when you have no association. So usually it's just where he kind of points all over the place. So just kind of like that maybe, right? Like if you were going to put a best fit line in that scatter plot, it's kind of hard to tell where it goes. Because I guess with the no association, maybe you'd think like, well, then that would go along with a zero slope. That is a type of no association, kind of a specific type, where then one variable changes and then the other one doesn't do anything. So yeah, you would say those variables don't have anything to do with each other, right? So it looked like they're not associated. And that is a way that you can have it, but usually if you have no association, it just looks like there's no pattern at all, and where there are just like points strewn about everywhere. But yeah, I mean, I guess you could have it where the points were just kind of like going left to right, because that would be a case where one variable clearly has no relationship to the other. But usually it is just points all over the place. All right, so then one way to quantify the association between two variables is to use something called the linear correlation coefficient. Most people just call that correlation. So when we go through this, whenever I talk about the correlation as though it's a number, really it's the linear correlation coefficient. But that's a thing where usually people just call that correlation. And it measures two things. It measures the direction, which you could argue that if you have the scatter plot, you don't really need that. That you could probably just kind of eyeball the scatter plot and figure out if it's a positive or negative association. And that's true. But if you had the data set but not the scatter plot for some reason, then you could still figure out if you have a positive or negative association by computing the correlation. Really, the correlation is a measure of strength, and you kind of get the direction for free. And the reason that you need a measure for strength is because you can't really do it based on a graph, because the way the axes are calibrated could make the exact same scatter plot look like it's a stronger relationship or a weaker relationship. So if you have a way of computing strength, then you don't have to worry about, well, are the axes calibrated weird and what I'm looking at is actually distorted? No. If you compute the correlation, it's going to be the same regardless of how you set your axes up. The one thing that is noteworthy, so I guess, yeah, it's really to measure strength, but this, which I had underlined already, that it's for the strength of a linear association. So if you have an obvious shape, but it's not linear, you might end up with a correlation coefficient that looks kind of weak. And that'll come back up later in the notes too. But that's a possibility because it really just measures the strength of a linear association. Specifically what I'm thinking of is if you have a sine wave. So like if you had something that just, and I guess here I have some space. If you had something that did this, like that's an obvious pattern, but it's not linear. And the correlation for a shape, like if you had a scatter plot that kind of followed that sort of pattern, it's pretty low. And that's just due to the fact that that's not a straight line, right? It's all curvy. So that's another thing that's worth saying about the correlation right off the bat, I think. And the notation, the sample correlation is R, not C, because C is reserved for like an arbitrary constant. So that's why it's an R. And then the population correlation, that looks like a P, but really that's a lowercase Greek letter rho, which is spelled RHO. That's the letter that is. So that thing right there, that is a rho. A lowercase one. An uppercase one looks exactly like a capital P. And the lowercase one looks a whole lot like a lowercase p. But rho starts with an R, like how sample correlation uses an R as its symbol. If you were going to do the correlation computation by hand, there's a way to do it. I wouldn't recommend that, but you can. So it's that. Basically. There's an alternate way of doing it, which if you're going to do it by hand would actually be easier. We're never going to do it by hand. If you look at what these are, the z sub x and z sub y are really z-scores, because since you have two different variables, each variable, at least like within your sample values, you'd be able to compute a mean and standard deviation. So you'd be able to compute a mean for x and a standard deviation for x. You'd be able to compute a mean for y and a standard deviation for y. And so then for each individual, you would have two measurements and you'd be able to compute two z-scores. So what you do, if you're going to do this whole thing by hand, is you compute both z-scores for each individual, one for the x measurement, one for the y measurement, and multiply them together. And you do that for every individual in your sample, add all those products together, and then divide by n minus 1, and that's your correlation. That has the potential to be a lot of work, especially if your data set isn't really small. If your data set's only like 6 or 8 points, then maybe this isn't the end of the world. But usually they're a lot bigger. And then it would take a really long time to do it by hand. So there is a way to do it in StatCrunch, and that's what we're going to use. Because otherwise it takes forever. So the menu you want is stat, and then if you go to regression and simple linear, and then just specify what your x and y variables are supposed to be. If you're just trying to get correlation, it doesn't matter which one's the x and which one's the y. But if you're going to do some of the other stuff, like get the equation of a regression line that we're going to talk about later, then you do want to specify the correct x and y. And it just shows up right here. So R correlation coefficient, and there it is. So like I put in parentheses to 3 places, that's 0.599. So just to show you where it is, since I've already got that data in StatCrunch, so I guess I don't need the graph anymore. But if you go to stat, regression, simple linear, and then x, well, we had duration on the x-axis, so I guess that's what I'll do. And then put int after, so like the amount of time until the next eruption on the y-axis, and then compute. And there you can see it. It's in that, I guess I wouldn't say table, it's in that list up toward the top above the table. It's called parameter estimates. And you can see where it says R correlation coefficient, and it's right there. Oh, the other thing is when you do this, notice up here next to options where it says 1 of 2. So like there's a second page. If you go to the second page, it's the scatter plot. See? And it's got the best fit line in it too, right? I mean, that's what that red line is. So if you want the scatter plot, usually this is actually the easier way to do it in StatCrunch, because you probably also want something off of this page too. We're never going to use this bottom table where it says analysis of variance for regression model. We are going to use the parameter estimates one. Not right this second, but we will get there. All right, so let's see what else we got. Properties of the correlation. The way it's computed, you can only get values between -1 and 1. The reason I put inclusively there is because it is possible to get exactly 1 or exactly -1, although it's very improbable in real life, because those are the strongest possible correlations. So basically the way it works is that 0 is the weakest possible correlation, and as you go farther away from 0 in either direction, the correlation gets stronger and stronger and stronger. To get something that's exactly 1 or exactly -1, you'd have to have the points arranged in the scatter plot in a perfect straight line, which is theoretically possible, but in real life, you don't see that. It's never that perfect. All right, so direction, sign of the correlation matches the direction of association. So positive correlation goes with the positive association, negative correlation goes with the negative association. So that's the part where you get the direction for free. This is the important part right here, the strength. So the closer the correlation is to 0, the weaker the association is, and the farther you get away from 0 in either direction, the stronger the correlation is. So then there is a part of that that's counterintuitive, or maybe not if you think about it in terms of absolute value. But if you just think about where the numbers are in a number line, it might feel counterintuitive. A correlation of, let's say, 0.6 would be weaker than a correlation of negative 0.7. Because negative 0.7 is farther away from 0. So that's going to be stronger. So that's the one thing you have to watch out for, and specifically it's when the negatives are stronger. It's easy to kind of make that mistake and get it backwards. So just be careful with that. Let's see. Then there's a bullet point about getting exactly 1 or negative 1 or 0. So 1 and negative 1, you have to have perfect linear shapes in the scatter plot. Not going to happen in real life. The only way to get exactly 0 would be to have a perfect geometric shape. Like if the points were arranged in like a perfect circle or a perfect square. That's not really going to happen either. You'll get ones that are really close to 0 if you just have points like strewn around everywhere with no discernible pattern. But to get exactly 0, in reality, that's a tough one to pull off. Correlation doesn't have any units. The reason for that, if I scroll up for a second, it's up there with the formula. So like this formula right here, that I just drew an arrow pointing at it, that's based on z-scores, right? That was what the z sub x and the z sub y are. Z-scores don't have units because the part where you divide by the standard deviation, you divide the units out. So if this thing is based on z-scores, which don't have units, then the correlation itself won't have any units either. So, all right, well there's that, and it doesn't depend on units of measurement, so that would mean like if you had lengths, like if that's what your data was, it was like a bunch of lengths, like that's what both variables were. Then if they're in imperial measure, like feet and inches, or if they're in metric, either way, you're going to get the same correlation. So that's good, right? If there are 2 different measurement systems in use for something, then the correlation will be the same anyway, right? That's what you want, right? Because really, whatever length you have, like whatever measurement you get in inches or whatever measurement you get in like centimeters, it's really the same length, right? It's just you're using a different unit to indicate, just some way of quantifying it, basically, right? But like if you have, like some table that you're trying to measure, like some rectangular table, how long it is doesn't actually change when you change the system of measurement, right? It's just the way that you sort of express how long it is would change. Let's see. Then the correlation commutes. So if you switch the 2 variables in the computation, you're going to get the same correlation. And I guess you could see that from the formula too. So if I scroll up for a second, if you look at that formula, if you interchanged where z sub x and z sub y were, you would get the same thing, because if you change the order of multiplication, that doesn't do anything, right? 3 times 2 and 2 times 3 are both 6. It's that idea. And then the last thing is correlation sensitive to outliers. Sure, because things like the mean are sensitive to outliers. And so then when you're computing a z-score, you use the mean to do that. And so then those are going to be sensitive to outliers. And then the correlation's based on z-scores, so it's going to be sensitive to outliers. Sure. So I guess kind of use the transitive property there. All right. I said the thing to watch out for was when you're thinking about like what correlation would be stronger, to kind of watch out for the negatives. So if we're going to put those in order from weakest to strongest, basically what you want to do is you want to start, like the weakest would be the closest to 0. Either way. So negative and closest to 0 or positive and closest to 0. And you just want to get farther away from 0, because the farther away from 0 you go in either direction, then the stronger the correlation is. So based on those 4, it looks like the closest to 0 is the 0.163. So R equals 0.163. Next farthest away is the negative 0.332. Then the next farthest away after that is the positive 0.849. And then the strongest is the negative 0.922. So there's the weakest. And then down at the bottom, there's the strongest. And you can think about it in terms of absolute value if that makes it easier, right? The absolute value of negative 0.922 is 0.922. So that's bigger than 0.849, which is bigger than 0.332, which is bigger than 0.163, right? So either if you want to think about an absolute value, that'll work, or if you just want to think about it as farther away from zero in either direction means stronger, that works too. All right, let's see. We've got some pictures here. So strong and weak are kind of relative ideas. Right? So like there isn't like an absolute strong, and you can see what the correlations are. They're like in the corners. So like here's a correlation of 0.9387. The second one, it's up here, negative 0.9249. The third one, it's down here in the lower right, 0.2985, and then negative 0.1132. And notice that these first two, these look really linear, right? Like if you were going to put a best fit line into those first two, you can pretty easily see where it has to go, right? Like here, you're just kind of going like right up through those points. Here, you're going right down through those points, kind of like that. Then when you get here, like you can kind of tell, it looks like here you probably kind of do something like this. This one's tough. I would think, probably kind of like that, maybe a little bit steeper. But that one's tough, right? Because there, the correlation's not very strong. The points are kind of strewn about a lot. So in a graph, stronger would be more linear looking, right? Where the points look more like a line. And those first two, they do, especially that first one in the upper left. But the idea of like what's strong and what's weak, that is kind of relative. It's not like there's some threshold, like some numerical value, where you could say like everything above 0.6 is strong, or below negative 0.6 is strong. What's strong and what's weak, it depends on the context a lot. But I mean, the idea of being stronger or weaker, like the farther away you get from zero, the stronger the correlation is, and the closer you get to zero, the weaker the correlation is. That concept still works. But what would be considered strong or weak is really context dependent. And it was in some other textbook that I used to have, which I don't think I have anymore. But it actually had a really good explanation of this, where there was it was something in biology, where in order to get a paper published, you had to have a correlation above 0.94, which seems really high. So then it's like, well, they're 0.92, let's say, which usually you'd think, oh, that's pretty strong. Like in that context, that's not that strong because it's not enough to get a paper published, right? And then there are some financial models where there's a ton of volatility and it's hard to get things that look like nice shapes in the scatter plot. So there are some financial models where everybody's getting like 0.12 and 0.14 and things like that. And then what if you had a financial model that had like a 0.2? It's better than 0.12 and 0.14, right? You get better predictions. So there, a 0.2 would be strong, and you wouldn't really think of it that way just without any context. But so the idea of strong and weak, context does play a big role in that. Let's see. Oh, and then there's the one with practically no correlation. And then you can see it up here. It's negative 0.0574. So, yeah, I mean, if you're going to draw a best fit line to that, where does it go? Right? Like, it's kind of hard to tell. Is it kind of going from the upper left to the lower right? Is it going from the lower left to the upper right? It's tough. Okay, so then finding correlation using StatCrunch if you had to type in the data. That's the idea here. So what we've got there, what I'm going to do, because I already have this in a spreadsheet, is I just made 2 columns because that's what you want to do in StatCrunch. Like if you had to type it in by brute force, I don't think you would have to on the homework. I think with the homework, there's always like that thing you can click in the upper right, where then you can copy the data over. But what I would do is I would just make 2 columns if I had to. So I'm just going to call them fires into acres. And so then with the fires, I'd have 72, 69, 58, and so forth. And then for the acres, 62, 42, 19, and so forth. The one thing that's really important here is don't change the order at all, because like for each column in this original table, those are different years, right? So like this is year 1, and then the second one is year 2, and then the third one is year 3, and so forth. I think this goes up to year 8. But then like the 72 and 62, they need to go together, right? Like they need to match up. And the way that you do that is that when you have the data in the spreadsheet, like either in Excel or in the StatCrunch spreadsheet, they need to be in the same row. So the easiest way to do it is just to copy the numbers verbatim. So just in the order that they show up there. So 72, then 69, then 58, then 47, and so forth for the number of fires. And then for the acres burned, 62, 42, 19, 26, and so forth. That way, the 2 values for every year, or every individual year, would end up in the same row. And that's what you want. You need those to match up. Otherwise, you'll get something that's not really what you're supposed to get. All right, so then we want to use StatCrunch here. All right, so let's do that. So in StatCrunch, what we're going to do is it's going to be the stat menu, then regression, and then simple linear. All right, so let's do it. I think I've got other data in StatCrunch right now, but let's get this out of here. So delete column, delete column. All right, now we're good to go. And I already have this ready to go, so I have it right here. And if I copy and then paste, that's what you would want it to look like. So if you had to retype data into StatCrunch, this is what you want to do. If you're going to put in headings, then make sure they're up in the headings, not in the first row. And then you just have your data in there. And then from there, and I guess you don't have to put in headings, you could just have variable 1, variable 2, but then you have to remember which is which. So if there's a way where you can kind of abbreviate the headings, in a way you sort of come out ahead doing that, because then it's pretty clear which is which, right? And if you use abbreviations, then usually you just have to like type in a few characters, right? Like fires and acres, those are little words, right? That's not a lot of typing to get them in there. But we want stat, then regression, oops. Oh, come on. Stat, regression, simple linear. And then the x variable and y variable, since we're just getting the correlation, it doesn't matter. I guess if you were going to make a regression model, it would probably be to predict the number of acres that get burned from the number of fires. So I guess x should be fires and y should be acres. But for the correlation, you could flip the order and you get the same thing. And then compute, let's see, and then where it says R correlation coefficient up toward the top in that list, looks like we've got 0.7705, at least to 4 places, that's what it is. So, all right, go back here. Looks like what we've got is that R is 0.7705. At least rounded off, that's what it is. All right. Let's see. The next thing that's in here is if you have a correlation close to 0, that doesn't necessarily imply that there's no association or really weak association. You could have something that's just nonlinear, where if you get like that sine wave type of shape, which is actually what you'd get out of this thing, right? Because temperature versus month, I guess presumably that's supposed to be the northern hemisphere. If like 1 is January, 2 is February, that kind of thing. But I guess it doesn't have to be. You just have to start in the middle of the winter, right? You could make it southern hemisphere. It's just that you start in July, right? But it's going to do that every year, right? Because that's what the Earth is going to do, right? Just based on the way that the Earth is tilted, right? During the year, you're going to get the warm in the summer, cold in the winter, warm in the summer, cold in the winter, over and over again. So you're going to get kind of a sine wave shape, and that's not linear, and the correlation for that would actually be close to zero. So if you don't have much of an association, then you should get a correlation close to zero, but in the opposite direction, if you have a correlation close to zero, it doesn't necessarily mean you have no association. It just means you don't have a linear association. You could have some other kind, like a sine wave. So that's one thing that could be going on if you have a weak correlation. Another thing is, what if you have an outlier? Watch this. This is crazy. All right, so the one on the left is the price and age of 10, and I'm not sure how you're supposed to pronounce that brand, if it's supposed to be Somerset or Somerset, but whatever it is, it's a bunch of houseboats, right? I'll just say houseboats, that way I can duck around pronouncing it wrong. So we have 10 houseboats there. The other one, there are 11 houseboats, because look at this one up in the corner. That must be like some like special vintage houseboat or something, right? Because age is on the horizontal axis and price is on the vertical axis, on the y-axis. So that's a houseboat that's really old but really expensive. Or that must be like some rare model or something that was discontinued long ago. All right? That would explain why maybe somebody would pay a lot of money for it. But watch what happens to the correlation. So the one on the left where there's no outlier, because that's what that is, right? Like there is a general pattern. You can see it. Like on the left, I'll just draw it in, right? Like the best fit line, it's going to kind of go like that, right? As the boats get older, generally they're not as expensive anymore, right? They depreciate in value. So the correlation should be negative, right? Looks like we've got a negative association there. Sure. What you get here is negative 0.930. Nice, strong negative correlation. Watch this. It's still going to be negative with that outlier up there in the corner. Negative 0.470. One outlier can do all that. It's not always the case that one outlier can have that huge of an effect, but when you have a little data set like we have here, then it can make the correlation go crazy. And that's what we're getting, right? That's a huge change, and it's just because there's that one extra point in it. Because that one extra point is so contrary to everything else that's going on. So like that's kind of crazy, but it happens, right? And I guess then what would you do like in this situation if you were analyzing data and this comes up? Then you'd have to think like, well, what do I do with the outlier? Should I leave it in there? Or if I take it out, is that actually going to be a better idea of what's going on? And that's just some weird anomaly that we're not really going to see that much, right? So I guess that's a context-dependent thing. And so like it says that note at the bottom, if an outlier is known to be an error, then you would throw it out. But otherwise, then you probably want to get both correlations, like with the outlier and without it, and then kind of say, well, how much does that outlier really factor in, not in a quantitative sense, but just like, I guess in a context sense. Like, are there a lot of these houseboats around where this happens? Or, like, is this going to be like a thing where there are a bunch of different models, like old ones that people really want and are willing to pay a lot for them? Or is this just like some freak thing that we're not really going to see? We're going to see it once in a blue moon. And then if that's the case, then the better model is probably on the left, right? If it's something where you're not really going to see it that often and we just happen to get one, right? And having one in there is almost like for a boat collector, it would be like winning the lottery that somebody had one. Then you're probably better off leaving that out of the correlation computation, because then what you would see the vast majority of the time would be more like what's on the left. But that all depends on the context, right? And I don't know anything about houseboats. I don't know if we should keep that in there or not. Um, but then the next thing that's in here is a test for the correlation. So we've had other hypothesis tests. We've had a test for a mean, test for a proportion. We can have a test for a correlation as well. And this is typically what you have. So the null is that the population correlation is equal to 0. So like it's always these. So these I'm drawing a box around right now. You could, in theory, have a one-sided alternative where maybe you're specifically looking for evidence of a positive correlation or specifically looking for evidence of a negative correlation. But the overwhelming majority of the time, you're just looking for evidence of some kind of linear association between the variables. So any kind at all, and that would be just if you have enough evidence to conclude that the correlation is not 0, right? If it's 0, that's no linear association. So the null is no linear association, so that would be a correlation of 0. And then the alternative, the conventional alternative, is some kind of linear association. And we're not going to worry about making it any more specific than that. Just anything, any kind of linear association at all. So that would be any correlation that's not 0. So if you look at how you would do the hypothesis test in StatCrunch, it's the menu that we were at before. So stat, regression, simple linear. It's just that make sure that hypothesis test is checked. And you won't have to adjust any of the settings. Oh, that's nice. So let's see. Did we have it checked? If I go back to options and edit. Yep. So the thing that's actually the important one is the one for slope. The test for the slope and the test for the correlation end up giving you identical test statistics and p-values, which, I mean, there is a proof for that where you would kind of go through like theoretically what the formulas are, and you kind of do some algebraic manipulation to change them around. You can turn one of them into the other one. So it does work, but that's the one that we're actually looking at. The test for the intercept, usually that's not terribly useful, but the test for the slope is the same as the test for the correlation. So where it says slope, those are the settings that you want, right? So just think, instead of where it says slope, I guess just pretend it says correlation, or it has a lowercase rho, right? Rho equals 0 for the null, rho not equal to 0 for the alternative. So yeah, we already had it set up right. So compute, and I should make this bigger because our table that we need is getting chopped off. So, all right. The thing that you want, it's in the parameter estimates table. You would want the p-value in the slope row. So that's the 0.0253, right? So like this is the one for the acres and the fires. The one that I have in the notes is for the houseboats. So we can do that one too in StatCrunch. So if I go back here, it's kind of small here, but what you want is you want to be in that row right there. So in the parameter estimates table, you want to be in the slope row, and the things that we actually want maybe would be these. So t-stat is the test statistic, and then p-value, well, I guess that's the p-value. And I guess we can go through and get this one while we're at it. Oh no, this is the this isn't the houseboats. This is the Old Faithful. Yeah, we can do that one too. All right, so let's see. We don't want fires and acres right now, so I guess we can get those out of here. And so just so I can show how you get the one that's in the notes, we'll do it with Old Faithful then. So copy and paste and stat and regression and simple linear, and we're all set. Compute. Oh, right. Select the variables. There. And then there they are. right? That 11.785, or yeah, roughly, that's the test statistic that's in the notes, and then the p-value less than 0.0001. So yeah, that's what we wanted to get, right? That's what's supposed to happen here, and we got it. That's good. All right, so then the important table, I made a nice big one here. So it's the one in the middle. So right, it's that slope row right there. And then the things that we may want are these two, because the test statistic and p-value in the test for the slope are the same as the test statistic and p-value in the test for the correlation. So test statistic, yep, it's that 11.785 roughly, and then the p-value is going to be really tiny. It should be with a test statistic like that, right? That's 11.785 standard errors above the mean. I mean, that's pretty far. So it's way, way, way out there in the right tail. All right, now we're going to do it for the houseboats. All right, that's the next example. I can see it peeking out there at the bottom of the screen. All right, so the houseboat data, which I also have in a spreadsheet. So we want to see if there's evidence of an association between price and age. So this is usually how that's written, but evidence of an association, you have an association, a linear association, if there's a non-zero slope, right? That's what we're looking for. So non-zero correlation or non-zero slope, right? Same concept, at least in terms of the test. All right, so let's do it. And I guess that means if I go here, now we can get rid of the Old Faithful, because now we're talking about houseboats. So let's see, where are my houseboats? In the middle. So I'm just going to copy these, and then I'm going to paste them into StatCrunch. So there's the houseboat stuff. All right, so then if we go to stat, regression, simple linear, it's really supposed to be set up to predict the price from how old they are. So even though this is really something for the next section, I'm going to make age X since that is what it's supposed to be. Don't have to change anything here, right? We got the two-sided alternative and the alternative hypothesis of the slope test. So that's what we want. And then there. So we can kind of see everything up in here where I think maybe it might be worth it just to kind of write down the parts that we're going to need. So I set it up where the dependent variable was price and the independent variable was age. So we will need that stuff very shortly. So it's worth at least pointing out now. So in the output, so the dependent variable is price, and then the independent variable is age. The next thing that's there, which we don't need right this second, but underneath that where it says price equals 426,631.31 minus 11,088.291 times age, we're going to need that. That's the equation of the best fit line. So we will need that shortly. That's actually for the next section. But this is one of those things where I think it's worth pointing out in a little in advance to be like, yeah, we need that thing later. So where it says price equals, so it's 426,631.31 minus 11,088.291 age. We will need that. Basically, that's a linear equation, right? Where if you think of age as being X and price as being Y, then you could see like, oh yeah, now it looks like algebra, right? But a best fit line, that should have a linear equation, right? The other stuff that we may need, let's see, the correlation coefficient, we've been talking about that. So the negative 0.930, even though we already knew that because it came up earlier when it was either include the outlier or leave it out. And then the R squared underneath, which is really just if you take R, the correlation, and square it. That actually tells you something too. That'll be a thing we need in the next section. So R, the correlation was negative 0.930, and then RSQ, which is really just R squared. That's going to be 0.864. And I guess the reason it's written with an SQ is because the output doesn't have a way to do like a superscript to write in an exponent. So the SQ is to make up for that. And usually that's how it works. Like most statistical software does not have superscripts. So it'll just say R squared, either as a full word or abbreviated. And then in the parameter estimates, there are some things that we need there. So let's see, let me section this part off just with a different color. So, right, because now we're going down to that table in the middle, where then what it looks like is that it has parameter and estimate are the first two things, and then there's over on the end of the table where it's got the t-stat for test statistic and then the p-value. And if I go back to where ours is, the parameters are intercept and slope, and then if you look at the estimates, they're the same numbers that are in that linear equation. Okay, that's the one I want. Okay, so it just says intercept and slope, and we have 426, 631.31, and then we have negative 11,088.291. So really, usually you have to pull these out of the table. So where it's written up toward the top, that's just like a convenience, actually, where it has it written out like it's a linear equation. But then what we had for the test statistics, so let's see, it ends up being about 10.501 for that one, and negative 7.134. And I guess we go back there, we can see them, right? 10.501, negative 7.134. And both p-values are really tiny, but those test statistics are really far away from zero, so they should be tiny. So, all right, back here, p-value less than 0.0001, p-value less than 0.0001. All right, so we're looking for evidence of an association between price and age. Well, the thing that you'd be looking for, so let me just get another color here. I'll just do this in black. That, right? Because you want to be in the slope row, and so it's that p-value. So, all right, what we're going to end up with is p-value. It's less than alpha for any reasonable alpha, right? Like that p-value is really small. Certainly less than 0.05 or 0.10 or 0.01. So then there would be enough evidence to conclude that the correlation is not zero, right? And that's what we're looking for, right? We have evidence of a non-zero correlation, which would be the same thing as saying is we have evidence of an association between the two variables, price and age. All right, let's see. I wrote too big up toward the top, and I had to write like almost into the next thing. So I guess this one very last thing here is that if you do have a non-zero correlation, or you have evidence of a non-zero correlation, that doesn't mean that a change in one variable causes a change in the other necessarily. That might be happening, but it might just be coincidental like it is here. Or it could be something where there's a third variable that causes changes in the other two, where it would look like they were sympathetic changes, but in the two variables you're looking at, it's not that a change in one causes the change in the other. But this is one where it's just sort of coincidental, right? The divorce rate in Maine versus the per capita consumption of margarine. Like, look at how well those variables match up, right? If you turn that into a scatter plot, it looks like they're going to line up very well. It would look very linear, and that would be a situation where you'd get a little p-value in your test for the slope / test for the correlation, and you end up concluding, oh, it looks like we got an association here. Okay, you might have an association there, and it looks like you would, but that doesn't mean that if you if somehow we're able to reduce the consumption of margarine, that would also reduce the divorce rate in Maine, right? That's not really the way that works. So, right, like those variables don't have anything to do with each other. So that is a thing that you can have. Oh, I forgot this is actually on here. It's not very big, but if you can read it, right here it says what the correlation is. The correlation is really, really high. It's 0.9926. So yeah, if you did the hypothesis test, like if you had the actual data and ran in StatCrunch, you're going to get p-value less than 0.0001 for sure. But that's, I mean, okay, fine, you have an association, but that doesn't mean that there has to be a cause and effect relationship. So that covers everything for section 10.1. 10.2 picks up with this. It's more stuff about regression lines, like the best fit line for a scatter plot and that kind of stuff.